Alright, we got AQA level chemistry, yeah, organic topic 11 pattern, yeah, all the amines pattern, you already know. Alright, come. Let's get into this. Alright, cool. Amines are direct derivatives, yeah, of ammonia, yeah. So obviously ammonia is NH3, yeah. And so an amine is basically just when you replace one of those H's on ammonia with like an actual group, like an ace alkyl group or whatever, yeah. So like CH3 or whatever, something like that. So you replace with the actual group, yeah. So they're produced when one or more of hydrogens in ammonia are replaced by an organic group, yeah? There are two types, aliphatic and aromatic, yeah? So on the left here, we've got aliphatic amine, yeah? And on the right, you got a thingy, bro. You got a aromatic amine, yeah? So aliphatic is like a chain kind of amine. It doesn't have to be a straight chain, but like a sort of chain situation. And then aromatic is when you got like a benzene ring or something like that, obviously, yeah? Uh, so aliphatic amines here, they come in a couple of types here. So they come in primary, yeah. So this is a primary one. As you see, NH3 would be ammonia, and one of the H's has been swapped for CH3. So therefore now we got methylamine, yeah. And this methylamine is a primary amine because obviously it's only got one coming out. Also, yeah, this aromatic amine here, phenylamine, yeah, is also going to be primary as well because it technically only has one group coming out as well because it's got HH and one organic group, yeah. So this is also primary, yeah. This one's secondary. As you see, the other H has now been swapped out as well for CH3. So now you've got dimethylamine. That's going to be a secondary, yeah. And then you're going to get tertiary, yeah. Tertiary is going to be when all three are swapped out for CH3. So you've got CH3, CH3, and CH3, yeah. So therefore you've got trimethylamine, yeah. Calm. You can also have quaternary, a quaternary ion, yeah. So this is when obviously as you know with ammonia, yeah, it can form ammonium ion, yeah, when another H attaches to it and it forms a coordinate bond, yeah. So here's the same kind of situation. If I've got a CH3, yeah, it's gonna donate its ammonia to it's gonna donate the two pairs of electron to that, yeah, and therefore the N is gonna become positive because it's gonna lose a lone pair. That's gonna become a tetra methylamine ion, yeah. Tetra means four, so that you've got four methyl groups, and it's now an ion, yeah. Alright, so amine base properties, yeah. So basically, amines can act as a base here. I don't know why that's. Oh yeah, shit. There we go. Alright, cool. So I was about to freestyle that. Alright, cool. So amine base properties, yeah. So amines act as a weak base because the nitrogen atom obviously has a lone pair of electrons here that can accept protons here. So if you can accept protons, that means that it's going to be a base here. So has a lone pair of electrons here. Alright, so if base strength depends on electron pair availability. Yeah, so the two electrons that are on the nitrogen, yeah, they can be more or less available. Yeah, depending. Yeah, and so the more available it is, the stronger the base. Because if it's more available, then they're gonna accept that proton easier because of coordinate bonding. Yeah, and so therefore it's gonna be a stronger base because it's accepting protons easier. Yeah, safe. Electron availability affects proton acceptance here. If electrons are easily accessible, the amine is more likely to accept the proton, yeah? That makes sense, innit? And a proton bonds to an amine via a coordinate bond where both bonding electrons come from a nitrogen's lone pair. So it's in topic 3 if you want to go check that out, yeah. That's coordinate bonding. It's explained over there or dative bonding, yeah, which is when two is a covalent bond that's formed when two electrons come from one single atom, yeah, onto the other one. Alright, cool. So here you got a form of covalent bond, so I'm trying to coordinate bond, so I'm trying to say. So you got the amine here, primary amine, methylamine. Got the lone pair there. We got H plus. That's going to be the proton, yeah. And so both of these electrons are going to be donated to the H plus, and the H plus will be accepted by N, and it's going to form a positive charge since N is going to lose the lone pair, so it's going to become positive now because you're going to have more protons and electrons, yeah. Alright, the inductive effect. So different functional groups here can affect how available the lone pair is, yeah. So whatever's attached to the nitrogen, yeah, that can actually affect how available that lone pair is gonna be, yeah. And this is by changing the electron density around that bond, yeah. So for example, alright, so here we got a benzene ring here attached to this, and now I'm gonna explain to you what happens here. So here we got a benzene, we got a like phenylamine situation here. So in this situation here, what's gonna happen is you're gonna get basically because it's so electron dense here, the ring over here, what's gonna happen, bro, is gonna be electron withdrawing, yeah. So these lone pairs here, they're actually gonna be pulled towards the ring, yeah, to go, join it. So it's gonna be pulled towards there, which means that's gonna withdraw electron density from nitrogen, yeah. So those electrons are now less available, yeah. So since they're less available, this is called a negative inductive effect, yeah. So because they're less available now, it's not gonna be able to accept a proton as much, yeah, compared to just normal NH3. You get me? So that's the situation there. So it actually becomes a worse here than NH3. Yeah. Now, if we look at a like an alkyl group that's attached to N, the alkyl group is going to have a carbon, yeah, and nitrogen is more electronegative than carbon, yeah. So therefore, carbon's electron density is going to be pulled more towards nitrogen, yeah. So therefore, nitrogen actually going to become more electron rich, yeah. So the lone pair is going to become more electron rich, yeah, and it's going to be a positive inductive effect. So it's going to be pushing more towards that way and more available, yeah. And hence that means that's easier to accept the proton, yeah. So it's easier if you got that situation. That's called positive inductive effect, yeah. Alright, calm. Alright, cool. So here, yeah, so you see benzenes draw electron density away, yeah. So as you see here, we've got a negative inductive effect here. Alright, calm. And here, alkyl groups here push electron density towards, yeah. And the more alkyl groups you got, yeah, the more positive inductive effect. So that means that alkyl groups here are gonna be highly basic here because they're obviously easier to accept a proton, yeah. And whereas arene group on the amine, yeah, is gonna be less basic here because it's harder to accept that proton, yeah. You get it? Yeah, so inductive effect that causes electron flow away from nitrogen here, and that decrease in electron density of nitrogen pair and basicity increases that way. This is normal ammonia, and then this is a alkyl, so like a methyl amine. It increase in electron density on a nitrogen lone pair, and inductive positive inductive effect here towards hydrogen. Yeah, alright, safe. Making aliphatic amines, yeah, so they are made in two ways, yeah, so either by reacting a halogenoalkene, yeah, with excess ammonia or by reducing a nitrile, yeah. So I'm gonna talk about halogenoalkene with excess ammonia, yeah, and this is to make the first to make a primary amine, yeah, you're gonna use a halogenoalkene with excess ammonia. To make a secondary, you're gonna instead of ammonia, you're gonna use a primary amine again, you get me? So use a primary amine, yeah, like methyl amine, that's gonna make a secondary amine when you react that with a halogenoalkene. You get. Alright, cool, yeah. Listen, bro. Yeah? Listen, my guy. Yeah? I'm gonna tell you something here. What we doing here? What we doing? Remind me. Somebody remind me, yeah? What we doing? Alright, yeah. So what we're doing, yeah, is I'm gonna show you, man, yeah, the production, yeah, of the primary aliphatic amine, yeah. So primary amine, how to make that, yeah. So this is gonna be our nucleophilic substitution, yeah. Pretty basic here. So we've got the CC, the halogenoalkane that you're gonna be using, yeah. Let's just give this one basic one, bro. Obviously we got delta positive here, delta negative there. Alright, safe. Now we got now we got excess ammonia, yeah. So there you go, that's there, yeah. And now obviously this is gonna be ammonia is gonna act as a nucleophile here, yeah. You don't need to put negative charge. It's gonna act as a nucleophile, yeah, because obviously these amines can act as a nucleophile as well as a base here. So it could ask you what's the role, and you'll say it's nucleophile, yeah. It's gonna be attracted to there. And then it's just standard, bro, nucleophilic substitution, bang, bang. That's gonna attach to there instead of CO, yeah. So now you're gonna get this situation. Lone pair got donated, so it's gonna become positive, bro. C is H, 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 H. And now obviously, what's gonna happen now is obviously, one of the H's is gonna fuck off, bro, naturally, bro. So that's gonna go into there. That's obvious, bro. Yeah. So this from the bond, the electrons are gonna go into the N plus because positive charge to reform that. Yeah, that's normal, bro, at this point. And obviously, the hydrogen can't just fuck off by itself. It needs something to take it away. So that's where the excess ammonia comes in. We're going to use another molecule of ammonia, yeah, and that's going to take away the H here. So it's going to attack that H and form a coordinate bond again to make ammonium, obviously, yeah. So ammonium plus. Also, as you can observe here, the Cl also got like kicked out here. So if the Cl is getting kicked out and you got ammonium ion forming, it's going to form ammonium chloride in it. So you're going to get H, C, C, NH2, H, 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 H. That's gonna be NH4 here plus Cl minus here. Listen, that's gonna produce a primary amine here. But if you didn't have excess ammonia here and you just did that and you produced a primary amine here, what you can do, bro, is you can use instead of ammonia here, you can use a primary amine. Yeah, if you use a primary amine and you do it, you're gonna make a secondary amine. Yeah, same way if you use a secondary amine and do the same reaction mechanism, you'll make a tertiary one, and you'll make a quaternary. That's the end of it. Yeah. So listen, bro, you can do the same exact reaction mechanism if it's asking the question. Instead of using ammonia, you can use any amine as well. There's no issue. Yeah, it's the exact same reaction mechanism. Yeah, so it's minor. Alright, Alright, cool. So here's what I was talking about, yeah. So we got primary or secondary amine, yeah, plus halogen gonna make our alkyl substitute amine, so like tertiary plus whatever the halogen acid, yeah. Alright, safe. Here's a similar situation. So we've got tertiary plus halogen gonna make quaternary, yeah, plus halide ions. So that's what I was talking about earlier, yeah. Alright, safe. And obviously, when it reaches final form, yeah, it's just gonna add to that halide ion as it is. It's not gonna be kicked off with anything else here. It's just gonna be together as a quaternary ammonium salt, yeah. Alright, safe. So the large number of possible substitutions here means that a mixture of products are produced here. As you see here, there could be very different substitutions using this method of halogenoalkanes mixing with ammonia. Yeah, obviously the ammonia, if it's not ammonia, there's no excess ammonia. It can also just react with more of the primary amine that you produced here to create secondary amine, like a tertiary amine. Yeah, so therefore there's bare possible substitutions here, and as a result, you're making a lot of like shit that you don't need. And so therefore, excess ammonia is used to achieve the primary amine. And so this method is not as efficient as possible. It's not going to get you a higher yield here, which ideally, if you're trying to make the most money here, be more profitable, you want the highest yield possible here. So the mixture of products can be separated using fractional distillation as well at the end. So it's a bit of a long process. So what you can do instead of that is you can just reduce it at nitrile to get it as well. So basically, the cheapest way to reduce nitriles here, there's two ways. The cheapest way is using hydrogen gas and a nickel or platinum catalyst there with a higher pressure and temperature. This is known as catalytic hydrogenation, yeah, and this produces primary amines only, yeah. So this is pretty simple. We've got a nitrile here, C triple bond N, and we got yeah, just hydrogen, bro. Like, what else you want me to tell you? That plus that hydrogenation turns into amine, yeah. Very easy situation, bro. Bait. Alright, cool. Reductions of nitriles, yeah. So a more expensive method is using a reducing agent like LiAO-H4, yeah, in acidic conditions, yeah. So you need to memorize that. That's in acidic conditions, and then that's the formula for it. And you need to memorize this equation here. They can ask for it inside the exam. You can also rewrite this if you want as well in a bit of a different way. You can write the nitrile plus 4 times H in brackets. H in brackets means a reducing agent, yeah. Same way how O in the brackets means oxidizing agent, yeah. Makes that, yeah. So it's the same thing, making an amine nitrile plus reducing agent and making an amine, yeah. The only thing I'll say here is that the reason why you got to put 4 there before the if you put reducing agent, it's going to reducing agent just represents H here. So because there's 4 hydrogens in the actual reducing agent you're using, if you want to write it like this way, you got to write 4 and then that bracket in it. But just stick to the top one and it'll be calm. But you also might see it like this. That's why I wrote it. Calm. Making aromatic amines here. So they are produced from the reduction of nitrobenzene here using concentrated HCl and a tin catalyst. You need to remember that. That's important, bro. This is done under reflux here to avoid losing reactant and product as they are volatile here. So again, this is an uncommon way that you'll see it is that nitrobenzene here plus 6 times reducing agent with SN and HCl is going to make phenylamine here plus water here. And this is in the previous topics questions here. If you go to that to the sheets here, and you go to that one, you'll see that this happened bare times here where you got to balance this. Bro, it's bait. You got oxygen, 2 oxygens removed, so oxygen's removed there, 2 oxygens, so that means 4 hydrogen, and you gotta have 6 hydrogen here, because 2 were left over in the on the ring, yeah? So therefore, that's why we've got 6 times reducing agent. The reducing agent you're gonna be using here is actually hydrogen, yeah? So this is the real equation, yeah? You might want to write this one down and use this one in the future, yeah? So this is nitrobenzene plus 3H2 with a tin catalyst and HCl gives you NH phenylamine and 2H2O, yeah? Memorize this equation because it can ask for it, yeah? Safe. And memorize those conditions as well, reflux and SN and HCl, yeah. And this is another way they can write it as well, yeah. Alright, calm. Nucleophilic addition elimination, yeah. So amines will also undergo nucleophilic addition elimination reactions, yeah, with acyl chlorides to make amides, yeah. They also undergo the same mechanism with acid anhydrides to produce an amide and a carboxylic acid, yeah. So I'm gonna show you the mechanism. Alright, calm. We've got an acyl chloride here reacting with ammonia or amine or whatever, doesn't really matter. I'm gonna do ammonia just to keep it simple, but amine is gonna be the same shit. So reacting it with ammonia, yeah. This can be nucleophilic addition elimination, yeah. So what's happening here? Nucleophile is gonna attack the C, standard, bro. The oxygen on here is obviously the 2 is gonna move on to there, yeah. That's gonna obviously break that bond here. So you're gonna have H3C, C, Cl is now down. Yeah, my man got added on here, so he's gonna be there. I'm write that as NH2. You'll see why in a minute. I'll write it like this. You can write it all separately if you want, doesn't matter. Uh, and then this is going to be one oxygen, yeah, one bond would got destroyed, yeah. Lone pair is now an oxygen, yeah, so do that. Alright, safe. This is going to have to reform, you already know. So you might as well just put that arrow in now. Uh, calm. Obviously, CL is going to have to be removed there. It's elimination, yeah. You already know this. CL is going to be removed. Normally something carries it away, but it's calm. You can see the hydrogen is going to be kicked off here as well. That can carry it away. So therefore, we got that situation there. As you see, this has become M plus now because it donated the lone pair. So because that's M plus, the electron's going to move from there to there, innit? So therefore, it's just going to do that. And now you're going to get the final product here, which is going to be H3C, CO, NH2 plus HCO, yeah. So you got nucleophilic addition and then you got elimination, yeah. Alright, save. So they're together like that. That's the reaction. Alright, listen, because I'm not a prick like your teacher, I'm gonna show you an actual example of like amine reacting with the acid anhydride, yeah, and how to do that kind of mechanism, yeah. Most people just tell you, oh, it's the same as the nucleophilic addition elimination with the chloride, yeah. Listen, I'm actually show you. So it is the same, but obviously, it helps when you actually like see it for the first time, you get me? So just draw the anhydride here. So we've got this AIDS right here. Come and then draw the amine here. Alright, safe. So obviously the lone pair here is going to be attracted to C, yeah. So same way nucleophilic addition elimination, yeah, and then that's going to be attracted to O, yeah. So exactly same as last time, yeah. And so now you're going to get C with one O there. The lone pair is going to be on here now. Going to be double that and negative. It's going to be ammonium is going to attach to that. It lost a lone pair, so it's going to be positive now. It's going to have still the CH3 there. The H is still there and the H is still there. It just got added like that. You're going to have CH3 here. You're going to have O over there, this whole situation here, OC, whatever. So just write that as OC. I don't really care about the shape and shit. Just do it like that, bro. Alright, calm. Safe here. So now what's the situation? Obviously, yeah, the situation, same way how CL got kicked off last time, yeah. This is what I'm saying, but it's the same, yeah. This is also gonna get kicked off, yeah, like last time, yeah. But again, that's not too obvious if you ain't seen it before, you get me? So, yeah. And then here, the NH here, again, same situation as last time, yeah, because plus here, this is also gonna get go onto there, yeah. So that bond's also gonna break and it's gonna attach to this shit over here. Same way how the H attached to the CL last time, yeah. And obviously this O is gonna reform that. So it's gonna go down there. So that's the reaction mechanism like that, yeah. And then let me complete it. So that's going to be CH3 here, C double bond O, N, CH3. So that's the N substituted amide here. And then it's going to be plus, and then this shit is going to be a carboxylic acid here. So H attached to all of this shit. So that's going to be H, C, H, H, C, O, O, H here. So yeah, that's it. So that's the actual reaction mechanism here with an acid anhydride and an amine here. Calm. Alright, so amides here. So you just saw an example of them here. They have a functional group of CONH2, yeah. So you got an amide here, which is like this situation here. So it's just carboxylic acid, but instead of OH, you got NH2. And here you got N substitute amide, which is like what we just created now. So that's again same shit, but instead of a H, you got an R group here, organic group there. So that's it. Alright, calm. Cationic suffocant, yeah. So quaternary ammonium salts here, they have long hydrocarbon chains here called cationic suffocant, yeah. The non-polar tail is attracted to oil and the polar head is attracted to water, yeah, like phospholipids, yeah. This helps oil and water to mix and remove grease from dishes, yeah. So it has this kind of structure here. You see the salt there, so you got the Cl minus, you got the N plus here. The N plus head is attracted to water as polar, and obviously this like carbon kind of tail, similar to like fatty acid kind of thing. is gonna be obviously non-polar, yeah, so it's gonna be attracted to oil and shit. So that's gonna cause like an emulsion kind of effect here, and that's gonna help it mix together. Alright, safe. They're also used in hair conditioner as well because they prevent the build up of static, yeah. Alright, cool. And that's the end of the chapter, bro. Alright, that's it.